Hello and greetings from Saarbrücken, Germany. My name is Dominik and I'm presenting a Coq mechanization of Trakhtenbrot's theorem I did together with Dominique. So let's look at the classical decision problem of first order logic. We can formulate it as, given the first order formula phi, is there a model M satisfying phi? Since the 1930s, of course, we know that this problem is undecidable in general. And this result, in fact, has been mechanized. We have presented it at last year's CPP. So the general fact is undecidable, that's okay, but are there fragments that are decidable? That's a question one can ask. And there are a few dimensions where one can restrict the problem and then look at another classification. So either one can look at syntactic restrictions, for instance, on the quantifier prefix, where very simple complexity indeed gives us decidable fragments. Or one looks at the signature of non-logical symbols, and here the general rule of thumb is that only binary symbols introduce undecidability in the first place. On the other hand, one can also look at semantic restrictions. And the restriction we're concerned with in this work is the restriction to only finite models. And here Trakhtenbrot has proven in 1950 that the finite satisfiability problem is still undecidable. And it's in fact somewhat dual to the general case where finite validity is not even enumerable, meaning that there's no complete deduction system for finite validity. So our goal is to mechanize this theorem in Coq. And what one does with such a project is one looks at textbook proofs and isolates a good proof strategy from it. And we have looked at textbooks, and here the proof strategy normally looks as follows. So one starts with Turing machines, looks at encodings of Turing machines as first order formulas over a custom signature introducing a lot of symbols. And then one verifies that the models of the formula correspond to the runs of the machine. And by this, we can conclude that M terminates if and only if phi M has a finite model, and hence finite satisfiability, if there were a decider, would induce a decider for the halting problem, which is of course absurd. But now if you use such a strategy as a base for a mechanization, then there are a few challenges. So first, here we use the custom signature, and typically in a textbook, reducing to the minimal binary case is even left as an exercise. And this always can mean bad things in a mechanization context. Then we need a mechanized model of Turing machines to first have a starting point of the reduction. And alone mechanizing a model of Turing machines is pretty hard in a proof assistant. But even worse, we have to in fact show that the reduction function is computable. So there, for instance, has to be a Turing machine encoding the function, translating Turing machines to formulas. Okay. So for this, fortunately, there's a very easy way out. And since we are using Coq's type theory, which is constructive, we can use a synthetic notion of computability, because every function that we can define in constructive type theory is in fact computable without needing to show a representation in a formal model of computation. So for instance, we can introduce some standard notions from computability without referring to Turing machines. So given a predicate P on some type X, we can state that the predicate is decidable if there exists a Boolean function in Coq's type theory that agrees with the predicate. And we can say it's enumerable if there's an enumerator from the nature numbers. And furthermore, given the second problem on some type Y, then we say that P reduces to the second problem Q if there's a function H translating instances of P into instances of Q. And in any of these cases, F, G, or H, they all need not to be encoded as Turing machines. So here we save already a lot of work. But you may ask, we still need Turing machines, right? Because the reduction I've explained to finite satisfiability and in the standard strategies, this was based on Turing machines. And now comes the second is, we're in fact working on a library of undecidability proofs. And a lot of undecidability proofs have been done already. Here's a graph, which is kind of an overview of the problems we have considered. You can also see it in my background. And here we see, for instance, Turing machines, but we also see another problem, PCP. And this problem, the post-correspondence problem, is the one we actually start with. Because the post-correspondence problem is a very simple domino-like problem, which only involves Boolean strings. So it's very easy to express in Cox type theory. And also it's very easy to encode in first order logic. In fact, at last year's CPP, when we considered the general decision problem, which is this arrow here in the graph, we used PCP for the encoding. So in our work, we just have to verify a reduction from PCP, and that's much more easy than doing this for Turing machines. Okay, so that gives our project an easy start. On the other hand, there's also complication, because we look at a domain that is not natural to represent in constructive type theory, because model theory is typically conceived in terms of set theory using heavily classical axioms. So on the fly, during this talk and during the project, we had to answer a couple of questions. For instance, what at all is a good rendering of models in type theory? What is the good rendering of finiteness? And even more critically, can we transport the tools that are typically implied in model theory to our setting? Or do we even have to invent other tools that help us deal with problems that aren't even visible in the classical setting? Okay, so let's start getting formal. I want to introduce first order satisfiability, how we represent it in our type theoretical setting. And I don't go much into detail. The only important thing is probably that terms and formulas are represented as inductive types dependent in a signature, which contains the function symbols and the predicate symbols. And then the syntax is defined such that we only have well-defined terms. So where function application and predicate application have term vectors of the corresponding arities. Then we define standard Tarski semantics, where a Tarski model should be consisting of a domain type D plus interpretation functions for the symbols. So one dependent function for function symbols and one dependent function for predicate symbols. And then we can do the standard trick of Tarski semantics. We evaluate into the domain and then lift logical operations into the corresponding logical operations of the meta logic. And with this definition, we can already give a formal definition of satisfiability, parametric in the signature sigma. And we say, yeah, we just ask whether there is a model and a variable assignment satisfying a formula. Good. Then we are concerned with finite satisfiability. So what is the notion of finiteness we use? And here we use the following. We say that a type is finite if it can be exhausted by a list. That's probably non-standard if one comes from a classical background, but in working in constructive type theory, this is a very neat compromise, because it's very easy to establish and work with. Lists are a central data structure. There's support in the standard library for it. So this spares a lot of headaches. On the other hand, this definition is pretty relaxed. So in particular, it doesn't enforce discreteness. So a finite type not necessarily needs to have finite decidable equality. And this means that establishing finiteness is a bit simpler. But on the other hand, finiteness is still, in this definition, a strong enough notion to give us some expected properties. In particular, that strict orders on finite types are well founded, and that for finite and decidable equivalence relations, we can always quotient onto some finite type. Okay. Now we can define finite satisfiability, and as one would expect, this means we require the domain to be finite, but also we require that all predicates are decidable, because a finite model should be nothing but a table where we can computationally look up all the data. For simplification, we also introduce finite satisfiability on a specific equality symbol. And here we require that the model interprets syntactic equality with real semantic equality. Good. So now let's look how we encode the post-correspondence problem in first-order logic. First, how do we define the post-correspondence problem at all? And here we use an inductive characterization where the post-correspondence problem starts with a set R of cards, and then it's about deriving pairs of strings from these cards. So a card is also just a pair of string, and then derivability is characterized with these two rules. So either we can derive any card that is a member of the set we start with, or if we have already derived something, then we can prepend every card from the set with it. And then PCP is just a question whether a match can be derived. Good, so what do we need to encode this in first order logic? First, we need a custom signature where we can encode everything we need. So in the function symbols, we need two constants and two unary functions where we can, such that we can represent strings. And then we need some binary relation symbols for derivability, for strict prefixes, and for equality. So strings are then represented as application chains. So this example here would encode the string false true. And the additional constant star signals overflow because we're concerned with finite approximations of solutions. And then we need formulas enforcing that the relation symbols are interpreted correctly. So at least the sanity condition on P is that it applies only to well-defined values. And the ordering should be indeed a strict ordering. And then there are also some sanity checks for F regarding overflow, disjointness, injectivity. It's not important to look at it in detail, but I want to make the point that this is all the information we need, and probably writing down the full reduction for a Turing machine wouldn't fit on a slide because there's many, many more corner cases to be considered. Okay, how do we go on? So now, given a particular instance R of PCP, we encode it as a formula, phi R, where phi R basically contains the axioms we have seen before, and then asks whether the model we are looking at thinks that there is a match. And the crucial part that I have to explain now is phi triangle, which basically encodes the inversion principle of derivability. So if we look back, we see that derivability had these two rules. So either we have direct derivability or composed derivability, and phi triangle makes sure that the model behaves similarly. So whenever the model recognizes that a pair XY was derived, then either this was trivial, just the encoding of one of the cards from the stack, or it is a composed solution where it's important that the model thinks that the smaller solution is indeed structurally smaller than the larger solution. And that's all. So now we are just left to verify that this reduction is correct, so that indeed PCP has a solution for the instance R if and only if phi R has a finite model. And we can quickly step through the proof. So let's see. From left to right, if R has a solution of length n, then we can look at the standard model of Boolean strings of length just bounded by n. So this is certainly a finite model, and we can show that it satisfies all the axioms, and it still, of course, it still accommodates the solution. So we get that it satisfies phi R. A bit more interestingly is the direction from right to left. So if we are in some finite model satisfying phi R, then we extract a solution from it. And the idea of what we're doing is that we just iterate the inversion principle until we have the full solution at hand. And iteration means well-founded induction on the ordering. And why is that possible? Well, because the type is finite, so the ordering is well-founded. Okay, so by now we basically have proven Trakhtenbrot's theorem. The only thing is that we are in a very specific signature, and what we actually aim at is the strongest result just talking about the binary signature. And for this, we give an abstract transformation of signatures that in particular applies to the previous one, but where abstractly we start with any signature which is finite and discrete, and also has arity bounded by n. And then what we give is a chain of reductions actually. First getting rid of equality, then merging all symbols into a single relation symbol. And then in the final step, we show that we can compress the arity which has increased over the previous steps back to just a binary arity. So let's look at all those briefly. The first reduction is in fact trivial and exactly as one would expect on paper. So we just have to axiomatize that the equality symbol is a congruence for all other symbols in the signature. And then we're done. The reduction in the middle is in fact yet another chain, but all steps here again are elementary. So basically what one does is one first encodes all function symbols as relations, then the relations are merged into a single relation. On the fly, some constants are introduced that we have to get rid of again. But everything is as one would expect. However, there's a little tumbling stone because some of these intermediate reductions here, in fact, expect the initial model to be discrete. And a model, because of our definition of finiteness, is not necessarily discrete. So there's an issue that we have to care about, discrete models. So by the notation f sub prime, we now mean that phi has even a discrete model. And the question is, do these two notions differ? Or the important direction, the question is, can every finite model be transformed to a discrete finite model? And in fact, the answer is yes, because there's a relation that we can quotient about. And this relation is first order indistinguishability, which says that x and y are indistinguishable and x and y are elements of the domain of some model if there's no formula and variable assignment that distinguishes them. And then a very, in fact, involved lemma is to show that this relation is indeed decidable, and it is also a congruence, which is not the hard part. I do have a backup slide on this if you have a question in the discussion session. But once we have this lemma, then everything is good, because then to show that f sub and f sub prime are indeed equivalent, we can just in the non-elementary direction, we can take the model which is the quotient over indistinguishability, and that this quotient exists was again mentioned earlier because it's a finite and decidable equivalence relation. Good. Then the last step of the reduction chain was compressing the n-ary predicate symbol into just a binary predicate symbol. And the slide before was basically an artifact of working in a constructive logic. So there we did not have computational access to equality deciders and so on. So there we had to invent work. Now we are on the other side of model theory. Now we are in a symptom of not using set theory, because in set theory this problem here is basically non-existing, because what a predicate is in the semantics is just a set. And then of course we can always reinterpret the question of the elements x1, xn being an element of the predicate p to be really the question, is this tuple an element of the set p representing the predicate? So to explain what's going on, just let's play as if we were in set theory, and then the reduction would, if one would even bother writing it down, look as follows. So we pick a set D representing the domain. Again, that's basically given if you use set theoretic model theory. And then we define a syntactic translation where predicate application is interpreted as mentioned above. And for quantifiers, we introduce the domain restrictions. And then we add to this translation a bit of structural requirements that membership is extensional and that the domain is non-empty. And then we verify that the reduction holds, so that in the original signature phi is satisfied if and only if in the binary signature the translation is satisfied. And even working in type theory, the direction from right to left is easy. We just have to extract the model. That's possible. But now the direction from left to right is really tough, because here we now really have to come up with a set theoretical model, which we can use to basically mimic the standard construction. Unfortunately, we didn't have to start from scratch, because in work of Smolka and Stark, we could use a Coq development of the hereditarily finite sets. And we can use a finite part of this, which is large enough to accommodate the model we start with, to compose a set theoretic model satisfying this need here. Okay, but this is, again, what I have talked about in the last minute will basically not be existing when working in set theory. Okay, and this brings me to the summary. In the paper, we give a full signature classification. What I have talked about in this talk was just the negative part, which we can conclude as soon as sigma contains anything binary, so either a binary relation or a binary function plus a unary relation, then we have a reduction from PCP to FSAT. So then undecidability is unavoidable. In the paper, we also complement this with the positive results that one can get. So if the signatures are monadic, then FSAT is decidable. And in any case, we can always enumerate all models up to extensionality. And so we can also enumerate all formulas that are finitely satisfiable. Okay, then I want to end with a few remarks on the Coq mechanization and on future work. So all results in the Coq in the paper are mechanized, so everything is made precise in Coq. And in fact, the paper is hyperlinked, so you can click everywhere, and then you can see the formal counterparts of every statement and definition. Then some stats. We roughly have 10,000 lines of code. And the interesting thing is where now we really see where the hard parts of the development lie. We have almost half of these 10,000 lines are for the last reduction, for the just compressing a relation to binary membership, whereas the main idea of Trakhtenbrot's proof is just 500 lines. So here it comes. This also stresses that our new proof strategy using PCP is really, really compact. So not only on paper, also mechanized in Coq. This is a very compact proof. Okay, and then just some further notes. So the engineering is pretty similar to as we have done it before. We use the Brown encoding of bound variables and dependent syntax enforcing well-definedness. More importantly, everything is completely axiom-free, so everything is also guaranteed to be computable and to be interoperable with any other larger developments, in particular the Coq library where our development has been contributed to. And here, just to finish with some ideas for future work, we plan to generalize the intermediate transformation so that they are not necessarily restricted to the finite case. We want to explore more of the direct consequences of Trakhtenbrot's theorem, study other undecidability results in first-order logic, and we want maybe to mechanize the classification with respect to quantifier prefixes. That's it. I want to stop with this slide, giving you some ideas and take-home messages for the discussion. Thank you very much.